Good morning to all of you. So we are discussing about the spectrum analyzers. So spectrum analyzer gives the spectrum of the frequency components, which gives the spectrum of the frequency components. And on the x-axis, it shows the frequency, and y-axis it shows the amplitude of the particular frequency signal. So the spectrum analyzer, it shows the output in the form of lines, okay, in the form of spectrum. Okay, so the basic types of the spectrum analyzers we are discussed are the spectrum analyzer based on the parallel filter bank analyzer, and a spectrum analyzers. So in the frequency, in the audio frequency range. So, and next, coming to the next type of the spectrum analyzer is RF spectrum analyzer. So the figure shows this figure shows the block diagram of the RF spectrum analyzer. So which mainly consists of a mixer, and IF amplifier, intermittent frequency amplifier detector. So here we have a display. So it is nothing but the CRO, and also we have sweep generator, voltage tuned local oscillator, which frequency is 2 to 3 gigahertz, and this RF spectrum analyzer can be used to analyze the signals in the range of from 0 to 1 gigahertz range. We can analyze the signals which are in the 0 to 1 gigahertz range of the signals. Okay, and here before applying to the mixer, so the input which is having different frequency components, frequency signals, so different signals which are having different frequency signals which are applied to the low pass filter, and for the low pass filter it allows up to the 1 gigahertz signals only. After that it will be stops the above frequency of 1 gigahertz. Okay, so after that the signal is applied to mixer. After that the signal is applied to mixer. So in the mixer, the 1 gigahertz signal, the signals which are below 1 gigahertz are applied to mixer, and the voltage from the voltage tuned local oscillator will be sent to mixer. Okay, applied to mixer. Okay, so here the voltage tuned oscillator will produce the frequencies in the range of 2 to 3 gigahertz. It produces the frequency ranges in the range of 2 to 3 gigahertz. That is tuned. That oscillations are produced based upon the sweep generator. So the sweep generator will produce the sweep output voltage, sweep signal. The sweep generator will produce the sweep output signal. So based upon the this applied voltage, so this voltage oscillator, or we can call the local oscillator. The local oscillator will produces or generates 2 to 3 gigahertz range of frequency signals, oscillator signals. Okay, and those signals will be sent to mixer. Okay, here the mixer is produces the intermittent frequency signals. Okay, here the intermittent frequency signals which are generated from the mixer are applied to the intermittent frequency amplifier. So here so the signals which are in the range of 2 gigahertz will be applied for the intermittent frequency amplifier. Okay, so here the amplifier in intermittent frequency amplifier having a range of 2 gigahertz. Okay, so here the mixer output will be amplified by using intermittent frequency amplifier, and that amplified signal is applied to the detector. So here this detector will converts that into the converts into the uh, so that converts into the voltage signal, and at that particular frequency it will shows the it will given to the vertical deflection plates of the CRO. So for the given the signal which is from the detector, so it is a voltage. The output of the detector is a voltage. So that voltage is applied to the vertical deflection plates of the CRT. So whereas the sweep voltage which is generated from the sweep generator, the voltage which is generated from the sweep generator is applied to the horizontal deflection plates of the CRO. So by applying the sweep generator to the horizontal deflection plates, so it will be acts as an horizontal. It will act as an frequency x-axis. So for the given for the obtained graph, the frequency on the x-axis, so that will be produced by the sweep generator, and the output of the detector will be applied to vertical plates. So then it will be produced as an magnitude or amplitude of the that particular frequency component. Okay. So like that, the each frequency components will be displayed as a that particular frequency, and its magnitude will be displayed at that particular frequency. Like this, the RF spectrum analyzer will be uh, produces the spectrum uh, spectrum of the frequency components. So this will be works in the range of uh, the input signals are works in the range of 0 to 1 gigahertz. Okay. So here the block diagram spectrum analyzer covers the range of 500 kilohertz to 1 gigahertz, which is called as super heterodyne time. The input signal is fed to a mixer which is driven by local oscillator. So the mixer is uh, the signal for mixer is from the input signal and the local oscillator. So based upon the frequency components is generated by the mixer, so it will produces the difference signal and the summative signal. Okay, so which are mixed with the which are based upon the local oscillator frequency. So from that we will get the frequency components of the signals which are present in the test signal. Those frequency components only detected, and those corresponding magnitudes or amplitude will be applied to the vertical deflection plates of the CRO, and from that we will get the amplitude of the detected frequency signal. Okay, and the frequency on the x-axis will provided by the output from the sweep generator. Okay. So same we are written here. So the local oscillator is nearly tunable in the range of 2 to 3 gigahertz. The mixer provides two signals at its output that are proportional in amplitude to the input signal, and frequencies which are sum and difference of the input signal and local oscillator frequency. So we told that so the mixer will provides two signals. So which in that the signal output signal is proportional to the amplitude of the input signal, and it produces the two signals. Those are nothing but sum and difference of the input signals. That is difference of the input signal and local oscillator frequency. So what we are seeing in the previous lecture is the mixer, not mixture. It is mixer. Okay, mixer circuit produces the difference and summation of the two input signals which are applied to the mixer. Okay. Based upon that, we will get the two output signals, and from that we will apply the intermittent frequency is applied to the intermittent frequency is applied to the intermittent frequency amplifier. Okay, the intermittent frequency amplifier is tuned to a narrow band around 2 gigahertz. This local oscillator is tuned to the range of 2 to 3 gigahertz. Only inputs that are separated from the local oscillator frequency by 2 gigahertz will be converted to intermittent frequency band. Intermittent frequency band and passes through the intermittent frequency amplifier. And it is rectified and detected, and it is rectified and detected, and it is applied to the vertical deflection plates of the CRT. And the sawtooth signal generator produces the frequency range of 2 to 3 gigahertz. So the tuning of the spectrum analyzer is a step receiver, which is shift linearly from 0 to 1 gigahertz. And this sawtooth signals is applied to horizontal reflection plates of CRT to form the frequency axis. And the spectrum analyzers are widely used in radars, oceanography, and this is biomedical fields, biomedical applications. So in the biomedical applications, I think we have studied in 3.2. So while obtaining the ECE waveform, we can get a number of different artifact sounds also will come. The different signals, including the electrocardiogram, ECG waveform. With the ECG waveform, we can also get other unwanted signals also will obtain while recording heart rate. Okay, so in such situation, that particular signal is having more than one signal, and other signals also having certain frequency. So, and those frequencies signals should be, so the amplitude and what is the frequencies, and those also should be to be known. Okay, so in such situation, you can choose this spectrum analyzer. So, what is the generated signal amplitude and what is the frequency of that generated signals? Okay, so how frequently it is generating? So that should be known by using our spectrum analyzers. So these are the this discussion about the spectrum analyzers. So spectrum analyzers are based upon the parallel filter bank analyzer and step receiver design, and third one is the RF spectrum analyzer, radio frequency spectrum analyzer. Okay. Next, the next one is digital Fourier analyzer. Digital Fourier analyzer. So with this digital Fourier analyzer, we can analyze the signals in terms of the Fourier transforms. So the basic principle of digital Fourier analysis is shown in the figure. So it is converts the analog waveform into over time period t into n samples. So it will be for time t, and n samples will get from the analog signal. Suppose assume that this is the analog signal, and which is applied to the fast Fourier transform processor, and it will produce us the different signals in the form of spectrum. Okay. So here the analog signal will be converted into the samples, number of samples based upon the time period. For a given time period, it will produce us the samples, and that samples will be applied to Fourier transform processor. So it will be converted into the form of spectrum. So here in the case of here, the CRT display is equivalent to a parallel filter bank analyzer having n filters with a bandwidth of 1 by t. 1 by t. So here this is the time period t, and this particular time period of signal will be divided into n samples. So I think all of you know the so how the analog signal will be converted into discrete signals. Okay, so here we have a discrete spectral response, so which is equivalent to simultaneously obtaining the output from n filters having a bandwidth given by delta f is equals to 1 by t is obtained by applying discrete Fourier transform to the sample version of the signal. So first of all, we will convert the given input signal into the corresponding samples. Okay, after that, that will be applied to the discrete Fourier transform. So we will get the spectral response by using this equation, and whereas S of k and delta of is a complex quantity which is obtained by operating on all these samples and by the complex factor, this the discrete inverse transform. So this is the inverse transform. So by using DFT provides both amplitude and phase information at a particular point in the spectrum. So discrete Fourier transform will provide both amplitude and phase information at a particular point in the spectrum. So in the particular spectrum, in the obtained spectrum, we can identify the amplitude and phase of the applied signal. Suppose the spectrum may be the negative. Okay, with respect to x-axis, the spectrum amplitude is maybe negative. So in such case, we can also identify the phase of the signal spectrum. Okay. So the discrete transforms are usually implemented by means of the fast Fourier transform, which is particularly suitable for implementation in digital computer. So in the digital computer, so most of the cases you can go for the fast Fourier transforms for the analysis of the discrete signals. And a digital signal analyzer plot diagram, which is shown next figure, which employs a fast Fourier transform algorithm. So this is the digital signal analyzer. So digital signal analyzer, it is using a fast Fourier transform algorithm. So this and it mainly consists of input section. It mainly consists of input section, control section, and display section. So in the input section, so here we have two channels, channel 1 and channel 2. Channel 1 and channel 2. So we will connect the signal which is to be analyzed is connected to channel 1. Okay, and that will be applied to the amplifiers. Okay. The input section signal is applied to input amplifier, and these input amplifiers are given to filters. There are two anti-aliasing filters are there. So this is 30 kilohertz and another one is the 300 hertz. So like this we have two filters. So the input signal is amplified and it will be applied to the filters. Okay, similar same type of the structure will be applied for the channel 2. For the channel 2 also we have an amplifier and two filters. Okay, and after that the filtered output will be applied to the 12-bit ADC. So 12-bit ADC, A to D converters will be converts the analog signals into the digital form. So that is in the 12-bit. The size of the output is 12 bits. So okay, and that is connected to, and that is connected to a multiplier. Okay, so in the multiplier, the signal will be multiplied with the sine or cosine, sine function or cosine function, and that is given to a digital filter. That is given to a digital filter. So and from there it will be sent to the control section of the fast Fourier transform processor. So here the fast Fourier transform algorithm will be included here, and based upon the applied data, it will be produced as the fast Fourier transform output, and that processor output will be given the display section. So here the display section will be applied to the CRT. Okay. So that signal will be applied to CRT, or we can also record that signal. We can display. For external CRT, we can also connect. So like this, we have the digital signal analyzer. Okay. So here the main purpose of this one is to analyze the. We can also analyze the correlation of two signals. Suppose we have to know the correlation and autocorrelation. To find the autocorrelation, the signal is applied to both the channels. The same signal is applied to both the channels. So with that, we can find the similarities with the same signal itself only. Okay. Whenever we have to find the cross correlation, so we can identify the similarities between two signals. So then those two signals, one signal is applied to channel 1 and another signal is applied to channel 2. So then we can find the with this process we can obtain the similarities between two different signals. So that is autocorrelation. Okay. So in this we have other options also, the common mode signals, and here we have external trigger. So we can also apply the trigger from the external, and internal trigger is also there. Internal trigger, and we have a noise generator. So with the noise generator, we can also analyze. So here it is given what we discussed previous block diagram. The block diagram is divided into three sections. That is input section, control section, and display section. The input section consists of two indicator channels. So we are seeing channel 1, channel 2. The input signal is applied to the input amplifier, where it is conditioned and passed through the two or more anti-aliasing filters. So the cutoff frequency of these filters are selected with respect to sampling frequency being used. So here the 30 kHz filter is used with a sampling rate of 102.4 kHz and 300 kHz filter with the sampling rate of 1.024 MHz. So here in the block diagram we have two filters. Okay. 30 kHz and 300 Hz. Okay. So for this we will set the sampling rate like this. Okay, for each filter, and the output of the filter is given to A to D converters. So to convert the signal into digital form, so a 12-bit ADC is easy. The output from the ADC is connected to a multiplier and a digital filter. So in the multiplier, the signal is multiplied with the sine and cosine. So from the output of the ADC digital signal, so that will be given to a multiplier, and after that it will be given to the digital filters. And similarly, suppose we have to find out the autocorrelation, cross correlation two signals. So one signal is applied to channel 1 and another signal is applied to channel 2. So here both the signals will be, here it will be the summation of both the signals will be occurs here. So with one channel we will get the information in this way, and another channel will be produces by connecting the switch to this lower 12-bit ADC, and both the signals will be sends to the control section. So with that we can find out the in the first Fourier algorithm, we can identify the similarities of those two, and from that we will get the output, and that output will be displayed on the CRT in the form of spectrum. So here we can operate this digital analyzer, signal analyzer, into two modes. The mode of analyzer to be used in depending upon the type of the mode. So here we have two types of baseband mode and band selectable mode. Baseband mode and band selectable mode. So two types of modes are there. So in the baseband mode, the spectrum is displayed from a DC to upper frequency within the bandwidth of the analyzer. So the baseband, so we can get the output in the form of spectrum, and that spectrum corresponds to from a DC to upper frequency. So higher values, very higher values, we can get the range of frequency spectrum of the frequency component. So from very DC or lower values of frequency to the higher values of frequency, very high values frequency of that analyzer bandwidth. So and in the band selectable mode, so band selectable means we have to select one particular band, which allows a full resolution of the analyzer to be focused in narrow frequency band. Suppose we have to analyze the signals in the narrow frequency band. In such situation, we can identify that particular band of frequency given a small band. So here it is narrow frequency band. Also, we can identify the frequency signals, and we can analyze that identified signal. Okay. So here we can use this digital signal analyzer in the two modes. One is baseband mode. So that is very high frequency ranges we can use, and also use in the band selectable mode. So for a particular given band, so suppose I want to find out the signals which are present in between, so 500 to 1000, or we have to find out the spectrum of the signals from 0 or lower values of the frequency to the higher values of frequency, very high frequency. So if you done the analysis from 0 to higher values of frequency, very high values, maybe 20 kilohertz, like that. So it is baseband mode. And suppose I want to analyze in a given band only, so that may be a very fine value. Suppose 500 hertz to 550 hertz. So in that range only. So you can also get the spectrum in this range also. So remaining range of frequency will be avoided. Okay. So like that we can perform or operate this particular analyzer in two modes of operation. Okay. So in the band selectable mode, we can go for the narrow frequency band. So narrow frequency band also we can get the proper output, full resolution we get. So after that, after conversion of the A to D converter, after conversion from the A to D ADC, the signal will be multiplied either by sine or cosine function. Sine or cosine function. Okay. And the processing section, in the processing section, up to now we have discussed about the input section, and coming to processing section, so of the analyzer provides FFT processing on the input signal. So that is, hello? So in the processing section, we have FFT processor. With that, we can using FFT algorithm. So the signals will be processed. Okay, and for one channel this can provide a real magnitude and phase. So it will provide the information of the magnitude as well as the phase. So in the real part we will get the magnitude and the imaginary part will get the phase. So we will get the information of the signals in the form of magnitude as well as the phase. So by using the two channels, we can also analyze the signals with uh, autocorrelation. So same signal is applied to both the channels. So in this case, we will apply the same signal to the channel 1 and channel 2, and finding the similarities with the signal itself. So and the cross correlation. So here two different signals are applied to two channels and determining the similarities of the two different signals. So you can find out the similarities of the two different signals. So that is the cross correlation. So in the output section, we will find out the similarities between two input signals using cross correlation. And similarly, in a particular given mathematical model, so we will apply the input and we will get the output. Suppose from the output to input, we will get the transfer function. So the transfer function is, so generally you can say it is a ratio of Laplace transform of output to the Laplace transform of the input. For the for discrete signals, so we can do the using this digital signal analyzer, we can perform the Fourier transforms. So Fourier transform of the output to the Fourier transform of the input. So Fourier transform of the output to Fourier transform of the input, and with that we can get the transfer function of the mathematical model. So that that gives the information of the amplitude and phase information. Amplitude and phase of the signals which are applied input and output also. So we will get the information. So how the output is changing with respect to the input due to the system. Suppose we have a system, a system is there. So we are applied some input, and from that input, so we will get the output. So to analyze the behavior of the given system, so first of all we have to convert that system into mathematical equation. So directly we can apply. Suppose we have a system. That system we apply the input in the certain frequency. We apply the input, sinusoidal signal is applied, and it is having certain frequency. By the application of the input signal, sinusoidal signal to a system, it may be thermal system, or it may be pneumatic system, or it may be electrical system. So due to some nonlinearity presence, the output is may not same as this one. So it may be produces some more frequency signals also, or it may be some distorted signals may be present. Okay, so how the response is changing from different operating ranges, we can analyze. Suppose we have a amplifier section. So by different frequency ranges, by changing the frequency, RC amplifier. Okay, so bandwidth of the RC amplifier will be changes like that. Number of amplifiers having different operating ranges. So after that, it does not provide the linear properties. So before certain frequency, it will provide the non-linear nature. After that, after the maximum value of frequency, it provides the non-linear properties. So below a band of frequencies, it produces the linear operating range. So due to the operating point variations, it produces the different variations in the output. Okay, so that can be analyzed. Okay, So the analysis of the frequency, you can say it is frequency analysis because we are applying some sinusoidal signal. Okay, and from that we will be getting some output. Okay, with these two inputs, how the output is changing with respect to input. So that can be identified. So for that, output of the amplifier is connected to channel 1 and input of the input which is applied to the amplifier is connected to channel 2. So with these two channels, the signals will be sent to the fast Fourier transform. There it will be using the algorithm, it will be processed and the output will be sent to the CRT screen. So there we can differentiate. We can differentiate how much it is amplified and from which frequency range to which frequency range it is get the proper output. And like that we can analyze uh, the properties of the amplifier or the characteristics of the amplifier. So like this, there are number of systems in the industries. So those like thermal systems, pneumatic systems, hydraulic systems, and electrical systems, electronic systems are there. So to first of all, to analyze these systems, we have to first convert the system into the mathematical model, the functionality of the mathematical model. So there are number of inputs will be there. Suppose we have a reactor in chemical process. So reactor is there. So for that we will send we will mix the material inside in the reactor. We will mix the material or mixing of the material. So with that mixing process, we can get some output. Okay, but mixing of that, so we have to provide some heat. Okay, and we have to check the temperature, and also we have to provide some water. So like that, there is some certain inputs will be provided, and by mixing process, it will be get some output after certain time of the processing. So in such situation, we have to identify so which parameter is influencing the to get the proper output. Okay, so for that we have to develop the mathematical equation. So based upon that, input and output. Suppose the temperature is increasing, what happening in the material in the reactor? The proper temperature is not maintaining in the reactor, so it will be the content in the material will be spoils. The formula will be changes. High temperature will be there. If suppose the temperature is very low, it will not be processed. So the processing of material is very important. So in such situation, we have to identify what factors will be influences more and what is the input and output. Okay, so for that we have to, from that concepts we will develop the mathematical model. So for that we will consider the number of like in our we have Newton laws. In mechanical will consider the Newton laws. Okay, number of equations will develop. Okay, from that we can first conversion principles. From that we can get the mathematical equations. For that mathematical equations, we can test different by giving the number of inputs. What is the output?